Is Multivariable Calculus, Chapter 12, Vectors in the Geometry of Space, Section 12.2, Vectors. So a vector is typically used by scientists to indicate a quantity, such as displacement or velocity or force, that has both magnitude and direction. A vector is often represented by an arrow or a directed line segment. The length of the arrow typically represents the magnitude of the vector, and the arrow points in the direction of the vector. We can denote the vector by putting a letter in boldface or by putting an arrow above the letter. For instance, let's suppose that a particle moves along a line segment from point A to point B. The corresponding displacement vector, as shown in Figure 1, has initial point A, or where the tail is, and terminal point B, where the tip is. And we indicate this by writing vector V is A, B. Notice that vector U, which is CD, has the same length and same direction as V, even though it is in a different position. We can say that U and V are equivalent, and then we can say this. The zero vector, which is denoted by the bold-faced 0, has length 0, and it is the only vector with no specific direction. Suppose then that a particle moves from A to B, and then so that its displacement vector is AB, as shown in Figure 2, and then the particle changes direction and moves from point B to point C with displacement vector BC, as shown. The combined effect of these displacements is that the particle has then just moved from A to C. The resulting displacement vector, AC, is called the sum of AB and AC. In general, if we want to start with vectors U and V, we first are going to move V so that its tail coincides with the tip of U, and define the sum of U and V as follows. The definition of vector addition is then illustrated in Figure 3 using the triangle law, and you can see, because the triangle is formed, why we call this the triangle law. In Figure 4, we start with the same vectors U and V as in Figure 3, and draw another copy of V and another copy of with the same initial point as U, and then we complete the parallelogram, and we can see then that U plus V equals V plus U. This also gives us another way to construct the sum, and this is called the parallelogram law. It is possible to multiply a vector by a real number C. In this context, we're going to call this number C a scalar to distinguish it from a vector. For instance, if we want 2V to be the same vector as V plus V, which has the same direction as V but is twice as long. We can also multiply by 1/2, or by multiplying by a negative number, we can change then the direction. Notice that all of these vectors are parallel because they are scalar multiples of one another. In particular, the vector negative V has the same length as V, but points in the opposite direction. And by the difference of two vectors, we're stating then that U minus V is equal to U plus the opposite or the negative of V. So for some purposes, it's best to introduce a coordinate system and treat vectors algebraically. If we place the initial point of vector A at the origin of a rectangular coordinate system, then the terminal point of A has coordinates in the form of A1, A2, or A1, A2, A3, depending on whether we are in 2 space or 3 space. These coordinates are called the components of A, and we can then write as shown here, that A is equal to this vector notation A1, A2, or we have A is the vector notation A1, A2, A3. This vector is then considered to be in standard position. We can think of all of these geometric vectors, though, as the representations of the algebraic vector A1, A2. As we see in figure 13, we have that vector A is OP, and that is the position vector of the point P, A1, A2, and A3. So let's consider any other representation of AB of A where the initial point is given by X, Y, and Z, and the terminal point I'm going to list as X2, Y2, and Z2, and we're going to label A as X1, Y1, and Z1. And so we can see then that X1 plus A1 must equal X2. Y1 plus A2 must equal Y2. And Z1 plus A3 must equal Z2. And therefore we have the following result, that AB is equivalent to A and is going to be X2 minus X1, Y2 minus Y1, and Z2 minus Z1. So when you are writing a vector using components and determining it from beginning point to initial point to a terminal point, you are subtracting where did you end up from where did you start. So therefore, as we have in example 2, we have vector AB is going to be defined as -2 minus 2, 1 minus a -3, and 1 minus 4, which gives us then -4, +4, and -3. So the magnitude, or the length of a vector A, is denoted by the absolute value bars or the double absolute value bars. We will use these interchangeably in class, and it's determined using the distance formula. So the magnitude of A is A1 quantity squared plus A2 quantity squared plus A3 quantity squared. So looking at example 2b, remember we have that vector AB is given by -4, +4, and -3. And so the magnitude of AB is going to be the square root of -4 squared plus 4 squared plus -3 squared. And so that is the magnitude of AB is the square root of 16 plus 16, which is 32, plus 9, so the square root of 41. Now, note that we could also write this magnitude of AB is simply -2 minus 2 quantity squared plus 1 minus a -3 quantity squared plus 1 minus 4 quantity squared. To find the vector sum A plus B, where A is the position vector given by 2, 3, -4, and B is the position vector given by -2, 1, 1, we can simply say that A plus B is going to be 2, 3, -4 plus -2, 1, 1, And so that's going to be 2 plus a negative 2 is 0, 3 plus 1 is 4, and negative 4 plus 1 is negative 3. And so you can see now we have vector A plus B. So given the components, we can then develop the following properties. If we have vectors A, B, and V, and C and K are scalars, we've shown that A plus B is equal to B plus A. We can, by addition of components, show that A plus the quantity B plus V is equal to the quantity of A plus B plus vector V. Any vector plus the zero vector is going to give you the original vector that you started with. A plus the negative of A, or the opposite of A, gives you the zero vector. The scalar C times quantity A plus B can distribute in, and it can become C times vector A plus C times vector B. And likewise, we can have the quantity of the two scalars, and I apologize, this should be a K, and this should be a K. So C plus K times vector A gives you C plus C times A plus K times A. Or if we have C times K times vector A, we can write that as C times K times vector A, and then the scalar 1 times vector A gives us vector A. So we have three vectors in 3 space that play a special role, and these are I hat, j hat, and k hat. These are the standard basis vectors, and they are denoted with the hat as opposed to the bar because they are the standard basis vectors and they are unit vectors. Which means then we can take any vector A, which we defined as A1, A2, A3, and we can write this as A1 I hat plus A2 j hat plus A3 k hat. So a unit vector is then a vector whose magnitude is 1 or length is 1. In general, if A is not the zero vector, then a unit vector that is in the same direction of A is given by 1 divided by the magnitude of A times vector A, or just vector A divided by the magnitude of vector A. And so remember, we have vector AB, we said was negative 4, 4, negative 3. We had the magnitude of AB was the square root of 41. And so then a unit vector is going to simply be 1 over the square root of 41 times vector negative 4, 4, negative 3. And we can also write that as negative 4 over square root of 41, 4 over the square root of 41, or negative 3 over the square root of 41, or negative 4 over square root of 41 I hat plus 4 over the square root of 41 j hat minus 3 over square root of 41 k hat.